In the last video, we looked at Karnaugh maps or K-maps in the fashion of a sum of products, and today we're going to look at the product of sums approach. So recall that a function can be expressed as a sum of products, where we have the summation and then all of our lowercase m's, which represent all of the min terms, and then we can also express it as a product of sums where we have a capital M, and then we have all the max terms that follow. Now if we have a K-map given as expressed below, the function of the K-map as a sum can be expressed as the second term, third term, fifth term, sixth term, and the seventh term. Now we know that that can also be expressed as a product of sums as the 0, 1, and fourth term. And we know that we have a relation between the min terms and the max terms with this inverse relation. So if we have a 0 at the location 0, 0, 0, which would correspond to lowercase m0, we know that we can take the inverse of that term using De Morgan's law and get w plus x plus y. So sometimes the K-map that you're given might not have the zeros filled in, you might only get the ones filled in, but if the values aren't filled in, assume that it is a 0. So the rule of thumb to follow here is that we take the zeros of the K-map and then invert them. And if we look at an example, again, with the same K-map, we can also express f inverse, and that's going to be equal to w bar x bar y bar plus w x bar y bar plus w bar x bar y. And then we can take the inverse of f bar. Now in our K-map, we're going to have a similar grouping fashion for the product of sums. So in this horizontal term here, we would get w bar x bar, and in this vertical term here, we would get x bar y bar. So we could also say that f inverse is equal to w bar x bar plus x bar y bar. Again, inverting this. So either using the ones or the zeros in the K-map are viable solutions. You just have to remember the trick with the zeros where you invert them. Now the last thing we want to concern ourselves with is the don't care conditions, where now, in addition to the ones and the zeros in the K-map, we simply have these lowercase d's, which symbolize don't care conditions. Now a don't care condition, simply we don't care about it. Either it's not possible from occurring or it provides no output that we deem necessary to consider. So if we look at this K-map, we can express it as a sum, simply by the first, second, third, and fourth terms, or we can express it as a product of sums. And then we have the don't care conditions in the 0 and 7 positions. And what we're going to do is look at the sum of products and the product of sums grouping, then build two individual circuits and see which one is best. And to do the groupings, we don't have to include the don't care conditions, but we can if it makes simplification easier. So if we look at the sum of products or groupings, we're just going to have this horizontal section of 4, and then this vertical section of 2. Now we don't include this don't care condition down here because we already include the one that it would group with. So if we look at this horizontal term, we simply get w bar. And if we look at this vertical grouping, we get x bar, y bar. So for the sum of products, we can simply say that f is equal to w bar plus x bar, y bar. So this is our first expression for f. And now we want to look at the product of sums. So we're going to group the zeros. And to group the zeros, unfortunately, we cannot group 3 terms together, but we can group 2 terms together. So we have one grouping here and another grouping here. So this first grouping, we get this term equal to w, y, and this second grouping, we get w, x. Now we're going to invert these, simply that we get w bar plus y bar, and this term we get w bar plus x bar. Now we multiply these together to simply get our other expression equal to w bar plus y bar multiplied by w bar plus x bar. And this gives us our second term. So what we want to do now is build each individual circuit. And by building each individual circuit, you can see that one of them is less complex than the other. It also has less components. So in this case, it would be better to go with the implementation using this function. Now maybe this isn't the case with each and every K-map, So you may have to go through the ones and the zeros to determine which circuit is best for your applications.